Good morning, everybody, on this beautiful Friday, at least here in Brussels. Welcome to the second webinar in our IAM-I webinar series. So we're still new to this. We're trying to bring you topics that are of interest and also overarching interest to the advanced materials community. As you know, today we have a special treat, and I can tell you some of you may know we recently, as IAM-I, co-organized an event with the EIC and the European Synchrotron Radiation Facility here in Brussels. It was an in-person event. It was an all-day event on a very similar topic, or basically the same topic. However, we realized that the interest in the community was so high to also gain online access to this kind of expertise. So we decided to ask the colleagues, the experts from the ESRF that kindly agreed to be with us today to come and present. I have one remark as to the organizational part. So Tobias, Schülli and Marta Mirolo will be giving their presentations. We will be doing the Q&A at the end of the session. In order for you not to forget your questions, please write them into the Q&A function that you have here at the top, not in the chat. The chat is for organizational topics only. Please use the Q&A function. And with that, kindly allow me to introduce both Marta and Tobias. And I will start with Marta because, frankly, when I read her CV, I found myself smiling because I came across a statement that she fell in love with the synchrotron world throughout her scientific career, which I think is a very nice and passionate statement for all of us scientists. So after Marta did her PhD at the ETH in Zurich, she started at the ESRF at the ID31 beamline. And today she's a junior scientist working in the Remade at ARI project. I hope, Marta, that is correct. You know, with abbreviations, it's so generally easy. She's responsible for the X-ray diffraction experiments dealing with circular economy in multiple facilities at the ESRF in Grenoble. And then we have the great pleasure of having Tobias Schülli with us, an absolute expert and specialist in X-ray physics and applied X-ray diffraction. He's a physicist and material scientist by training, so no one better than Tobias to speak to us today. He holds a PhD from the Johannes Kepler University in Linz, a postdoc at the CA in Grenoble. And after a position in industry, Tobias joined the ESRF in 2009. And since 2025, he leads the X-ray imaging and microscopy group and is responsible for an amazing amount of 10 beamlines. And with that, just to keep it short and sweet, Tobias, please, the stage is yours.
Thank you very much for this introduction. I almost wondered whom you were talking about, right? Very nice. So I'll hopefully this is going to work. I'm going to share my screen and presentation mode. Bang. Okay. Does it work? You see presentation mode? Very nice. Good. So it's really a pleasure that we have this opportunity to share our experience and expertise and show you some highlights. So Marta and myself are really excited about that. I start with a short introduction on, let's say, what are these light sources we're talking about and where we're working, and we both spent decades of our lives, right? So these are synchrotrons, right, where we are working, and they're multidisciplinary light sources. This is the way to say it. So what is a synchrotron? These are particle accelerators. So many of us have heard of these, even the layman has heard of this CERN. CERN, everybody knows CERN, right? There's a photo of CERN here. And well, some of these are used to study particles indeed, and particle physics. And that's the historical origin of synchrotrons. But today, most of them are built, the overwhelming majority are built as light sources. So these particles lose energy in the form of light. And that turns out to be the most brilliant and most powerful and actually even most energy efficient way to produce X-rays and even UV or even visible. But what we're talking today about is essentially X-rays, right, which are produced at facilities like, for example, the European synchrotron that you see here, right? And that light, these X-rays and even the UV, right, can use for anything, right? The fact of being a light source doesn't mean you know what you should do with it, right? You can do everything with a brilliant light source, and that makes these synchrotrons eventually the most versatile and multidisciplinary research hubs, right, that were ever built, which is another actually very, very exciting characteristics of a synchrotron. You meet all areas of science. You meet from paleontology over cultural heritage, medicine, material science, electronics, quantum physics. You meet them all, and they're all running in parallel because a synchrotron runs many beamlines. So there's always 30 or 40 measurements in very different disciplines running in parallel. In addition, over the last 4 decades or 5 decades, synchrotron radiation, the technology of synchrotrons, has had an exponential progression, which has even outrun, in terms of the basic performance parameters, has even outrun Moore's law, which we associate with the revolution in microelectronics, right? That tells us something, right? We all know how everything we've lived through the 80s, 90s, how every computer 5 years later dwarfs everything that we knew before, right? With the synchrotron, it's been like this, but even worse. So that means it's a particular challenge even to anticipate all the possibilities we'll have in 5 years. It requires a lot of vision, and always means they're eventually always underused, right? So if you have a good idea, it's always likely to work out much better than you thought, because the time it takes to bring it to the synchrotron has already improved. So this is something really fascinating. I also had the privilege actually to live through over the last 25 years at least. And another remarkable fact, and this is particularly pertinent in Europe, right? Europe has the most densest network of such light sources, and we're even really organized Europe-wide, which is actually, well, at least something, right? We're organized, and it means every citizen of these 550 million people can access to a light source, right? If we're motivated and write a proposal. And the light source network, LEAPS, which is the League of European Accelerator-Based Photon Sources that, in principle, Marta and myself present today, right, is actually the largest network worldwide of such analytical research infrastructures. And the idea is to give you access to synchrotron radiation in the most efficient and best way, right? We're not fighting each for ourselves, where every facility has its specialty, meaning there is over 300 highly specialized end stations available. And if you speak to an expert at one facility, he or she will even likely tell you, well, you should go to the other end of the continent where you find your facility. And this network today also means our user community is mixed and they know each other. And we have over 35,000 users, and hopefully after these seminars, let's say 100 more, right? Good. So this was the introduction of these light sources, accelerator-based light sources, and now I give an overview of examples on operando and in-situ characterization of electronic devices. I'm going to start, of course, this can never be complete. I can't present you 300 end stations, right? So I'm going to limit myself to a few examples that I know well and that have proven to be very pertinent for electronics in the past. So a technique I start with is scanning nanobeam diffraction. So if you have a nanobeam, you focus a beam on a synchrotron on a sample, you do diffraction, which means you harvest a Bragg peak. That Bragg peak carries information on the lattice parameter in your sample, your crystal structure. And then you scan pixel by pixel, you make an image. And in that image, you can then see spatially resolved, right? The variation. So this has been done on a silicon germanium buffer, which was a novel kind of substrate more than 10 years ago and is still used. This was one of the first industrial applications of this scanning diffraction microscopy. And you can trace images then of the variation of the heterogeneity of your sample, which is very important, right? What you can image is the lattice orientation, for example, down to a thousandth of a degree of change in tilt of your crystal lattices, and a strain resolution down to a sensitivity down to 1 in a million. 1 in a million of a distance between atoms, right? This is very, very precise. And the spatial resolution now well below 100 nanometers. So this is where we are today, and the applications are multiple. So this sensitivity is actually particularly fascinating, right? What does that mean? 10 to the minus 6 resolution or sensitivity to lattice parameter, that is actually a mouse tiptoeing on steel. So that mouse here with on the toes, right, will compress the steel, the atoms in the steel, by 10 to the minus 6. And we could see this in theory, right, with our nanobeam if you would look here, right? So this is the sensitivity where we are, the compression a mouse causes to steel. You may think that's not the first application, right? Nobody worries about steel being worn by mice trampling it, but the sensitivity says a lot. And actually, it is a useful sensitivity. So I start with the first example, which is a silicon quantum well for silicon qubits, right? This is a technology where Europe eventually has the edge, right? The silicon germanium quantum computer is likely to emerge in Europe. And so what is this about with the strain? The effective part of the quantum computer where the qubits will be generated is this 10 nanometer silicon quantum well, which is sandwiched in between silicon germanium alloy parts, which strain that quantum well. And we need very homogeneous strain. So now this quantum well is buried deep in the device. Well, in diffraction, electronic devices typically are layered systems. X-rays penetrate the whole sandwich, but then as the layers are out of different materials, often enough, right, they scatter, so their Bragg peak is slightly somewhere else in angular space. So depending on the spot I choose on my detector, I can only look inside one of these layers and choose to be blind for the rest. And this has been done here. So people have analyzed only the silicon quantum well by shining through the whole sandwich, and then mapped in 2D, so this is a two-dimensional map, the homogeneity of strain. And of course, we see a lot of structure here. And this, for example, are the electrodes on top of it here, right? But this is not a shadow of the electrodes. What we see, as this has been done under operation conditions at cryogenic temperature, right? The thermal contraction of the metal electrodes leads to strain that reaches down to the quantum well. And that is very critical for the functioning of the device, right? So, and this is the only method to measure that, right? To keep the device intact and measure the strain only in that very thin layer here by reaching out it with X-rays. So this is a very, very relevant result for the development of silicon qubits. Now we want to speak about operando imaging, as that's the idea of this seminar. And there is another aspect of this 10 to the minus 6 resolution that would correspond of the thermal expansion corresponding to a few Kelvin in a semiconductor. So that is what we can extract also with that sensitivity. And the method, we're swapping a bit, right? Instead of nano focusing, we illuminate the whole device with a beam, and we put the optics in the diffracted beam. So we go to a Bragg peak, and then the Bragg peak, we image it on the detector. So we get a 2D image in one shot of what is diffracting and what isn't. So that is called a dark field X-ray diffraction microscopy. The advantage of this is, well, we get an image in one shot, and we can also look at dynamics, either of temperature slowly increasing, but I right away go maybe to a more exciting example. We use the very high time resolution we can achieve with the electron bunches of the synchrotron. Because in the synchrotron, the electrons are traveling in bunches. There can be hundreds of bunches, but this is just an example here. But in this example, there's only 4 bunches. These modes exist. There's many modes. And these electron bunches, they're only 3 millimeters long, so they're very tiny, traveling at the speed of light. That makes about 100 picosecond length of these electrons, which means every time they pass by one of these multiple beam lines, they leave a 100 picosecond light flash, okay? And then in between these bunches in that mode, I'm taking the ESRF as example, there is 210 meters, so there's a long time in between these bunches. This is 700 nanoseconds. So speaking about electronics, typically, imagine I put a device on such a beam line here in that beam, and I make an image, diffraction image of this device. And I switch it on. I apply a voltage. I switch it on. On switching, whatever it is as device, it'll take a few nanoseconds, for example, right, for the voltage to become stable. Then I've switched it on. During that on switching, I come in with a 100 picosecond light pulse, which is very short compared to this nanosecond process. And then as it's 5 nanoseconds switching it on, I can switch it on again because I have 7, I can wait a long time, right, for it to be switched off again. And I switch it on again when the next bunch comes. But maybe I switch it on in a way that the bunch hits this switching on curve somewhere else. And I can sample this curve on all interesting points, let's say, and get an image on all of this whole switching process. I can make a film of this whole switching process, right? By synchronizing things well, but synchronizing electronics is actually very easy. Yeah? And an example for this is, for example, here, germanium tin laser. These are new light sources that can be integrated in with a standard silicon CMOS technology. So these lasers are out of germanium tin alloy. They have lots of defects. So this is a diffraction imaging analysis of this device. I want to talk about when we use this device. So this is a film where we've switched this laser on, got a light flash, imaged it, and switched it on again, etc. And so we have to assemble the film, right, of the whole switching process, which is here even tens and hundreds of nanoseconds. And what we have done, the measurement, the lattice parameter measurement, we have converted it into temperature, right, because we can see temperature changes, right, because we see the lattice changes. And while we show this film, in principle, the current should come in all along this semicircle here. But we see the pattern here of heating, of warming, it's only a few 10 Kelvin, right, is spotty, right? So it means there's hotspots. The current does not come in homogeneously, well, which means there's hotspots. This is certainly something which is important if you want to understand the degradation of the device. Right? How often we can switch it on, or how long we can drive it, depends on how the current flows through the device. So this is very, very relevant and uniquely accessible with that method. Next example, in a similar manner, right, we've been switching a high power transistor. So that was a work in collaboration with Infineon and other partners in the framework of the ATMO Power European project. And so that is a gallium nitride high electron mobility transistor we want to look at, a HEMT. These transistors are the power supplies of your mobile phone, your computer, etc., to convert voltages. And we look at the large 2D regions of these elongated channels here of the transistor. And of course, we look at different angles. As this is a layered system, right? A complex device. Depending on what scattering angle we look at, the diffraction contrast may change because what we see is not always the same layer, right? So by changing the angle, making an angular scan, right, in 1 pixel. So people who've done XRD in the lab may know such scans here. So this is the scattering angle we look at. And then we can identify the materials because these are just different lattice parameters. So we can, for example, see here the gallium nitride, the buffer, aluminum gallium nitride buffer. We can see a superlattice, which is kind of transition layer on this silicon substrate here. And we can see the tiny aluminum gallium nitride barrier, which is very weak because there's actually a very thin layer, right? This is not to scale. So a very thin layer, this is the active part of the transistor, right? And we can select it by going to this scattering angle here and then look at the image and then switch the transistor and see what happens during switching, okay? So this is what we have done. And of course, we can repeat this then for every incoming pulse and little by little look at the entire switching curve, right, as in the previous example. So these are these elongated channels here of the transistor. We see already there is some structure here because there's always a bias applied. And then we can look here, the nanoseconds are running, right, and we can, of course, see there's dramatic changes. So this is just a strain, and blue is compression, red is expansion, right? So we get even reversed signs of strain during this voltage curves here, which describe the device switching. Right? Without going into detail, this is in itself a long paper, right? There's a very, very large set of data, three-dimensional information in reciprocal space in every pixel here, and that allows us to extract a lot of information, and notably here, it allows us to separate effects that are related to heating and effects that are related to piezoelectricity in the aluminum gallium nitride. So the fact that this is a piezoelectric allows us to see the electric field in the transistor during functioning in real time. So this is absolutely fascinating and only possible with that method, right, in the functioning device. Of course, where results are about to be treated, and you're gonna see this appearing soon, I hope, in Nature Electronics. Yeah. So if you go to something faster, now we've been switching many nanoseconds. Imagine you have a gigahertz device, right, that you don't want to switch on, you just want to see it running while it's running. Well then, whatever your bunch structure, you can still synchronize your device with the bunch clock of the synchrotron in a way that if your device is very fast compared to the synchrotron, you still make sure your pulses always hit the device at the same phase. So here you always hit the summit of this voltage curve, so you get an image a static, stroboscopically static image of your device at that point of the cycle, right? And then you can shift. You look at 0 volt, right? And you always hit it at the same cycle. So you can assemble images, and you can assemble a video in the end over the cycling of the device. We have done this here with a surface acoustic wave device. These devices serve as radio frequency filters in your mobile phones. Very, very nice sensors, and there's a lot of very creative applications. They're typically printed electrodes on piezoelectric substrates. Here, this is lithium niobate. People work on a bunch of materials to make these cheaper and better, and come to our beamline actually to look at them. But now, well, this is a quite fast device, and if we're excited always in phase with the synchrotron, as I said, we can sample the entire cycle. And we can get, here we see a static stroboscopic image of such a wave. What we see here is the strain, right? So we have a few 10 to the minus 5 only. So the differences here in interatomic distances is 1 in 100,000, but this makes for us a very strong contrast. And we see where the wave is running, right? And this is an assembled video with 150 picosecond, in that case, time resolution. We see here a nice standing wave. And then we see a leakage modes here. We see, so the device is designed for that standing wave, and here we have all the leakage modes. And the nice thing is here, we measure the strain quantitatively. That means we could calculate the elastic energy here per atom. And that means we see how much energy is leaking here. We can quantify the energy leaking out of the device here. So this is also something, no way to do that with another method than diffraction imaging. And I stay with the surface acoustic wave devices to lead over to a totally different method, right? I try to avoid to confuse you with too many methods, but as I said, these light sources, they can do almost everything, right? And now at least I keep the device, so I keep the topic, right? And I swap to something completely different, no longer diffraction, but some spectroscopy. So I shine in here. So this is an example from Alba Synchrotron in Barcelona. With a soft X-ray beamline. So these soft X-ray beamlines, this is extreme UV to soft X-rays. You can't do diffraction with these wavelengths. So typically you do core level spectroscopy, you excite atoms and you look what comes back, right? But what we can do here is we illuminate a sample with a big beam. Then on this beamline, one can do X-ray photoelectron emission microscopy. So there's photo emission from your sample because you hit it with high energy UV, right? And so the photoelectrons that get ejected, they get channeled through an analyzer and electron optics, and you make an image. So you see what is emitting from your sample and what isn't, right, on the sample surface. This is very surface sensitive because the electron escape only on the narrow surface area. So if you do that with a surface acoustic wave device, okay, here people synchronized it entirely with the Alba synchrotron. So this is a bunch mode where you have 500 megahertz. You have a bunch every 2 nanoseconds, but the bunches are very short. They're 80 picoseconds. So you synchronize the device that you hit it, for example, always at a voltage summit, right? And then you get a kind of static stroboscopic image where you see the traveling wave, but you see it always in the same shape. And you see dark and white areas here. Where does that come from? Well, you have a piezoelectric, right? So this wave traveling at the surface of this piezoelectric generates a piezoelectric field, which means if you shine light on it and you rip out electrons, then these electrons in one area, they may get accelerated, and in another area, they get decelerated because the electric field is reversed in your piezoelectric. That means they come out at different velocities, which means the electron analyzer will filter them, and you get only electrons at a certain energy arriving on your screen here. And that means if you have the right energy, you see the wave, right? Then what you can do very elegantly, you can apply a voltage to the sample, right? And then with changing a few volt, the total electron energy, you may shift of what you see and what you don't see, okay? So people have done that here, and it's within a few volt, this image here, right, turns to kind of the reverse. So in the red square here, we are black, and here we become bright, right? This is because this is just this few volt difference that the piezoelectric field does to the electrons, and you just change it with your bias. So in that way, the nice thing by doing so, you can measure exactly the voltage, the field strength, right, of your piezoelectric. So if you know your piezoelectric field, you know exactly the deformation if you know your material. So that is another way of extracting the strain, information about strain, just by tuning a voltage. You can measure the strain in your wave. this is, in addition, extremely surface sensitive, right? So what you see really happens at the surface and not in the bulk, which can be an advantage, right? or a downside, depending on what you want to look at. But this is a totally different way of looking at the same phenomenon, right? And you extract different information from the same device eventually. So we stay with this spectroscopic approach, and this is my last example that I want to present you. This is a resistive switching material. So this is less a finished device, it's still on the material science side. So strontium cobaltate, okay, is a material eventually that could eventually be a resistive switch, right? Resistive switching means you apply a bias to your material and you change its resistance. So that happens with the strontium cobaltate. Here the sample is strontium cobaltate on strontium titanate and then covered with a top electrode, which can be gold or strontium ruthenate. And then a first experiment was done at the Bach beamline at Elettra Synchrotron in Trieste in Italy. Again with soft X-rays, so this typically 1 keV soft X-rays. You scan the X-ray energy, you excite atoms, and you measure how much fluorescence comes out of your sample. And then if you scan the incident photon energy across an absorption edge, you typically get a peak, right? And so here people selected the cobalt edge, right? Because you want to be sensitive to this layer only, right? So you penetrate, you excite also stuff in the upper layer, but cobalt is only in that middle layer here. So if you look at what's happening at the cobalt edge, you're sure it comes from this layer. So people scan across the cobalt edge and then apply a bias. And under application of bias, we see a few electron volt shift, right, of this cobalt edge. And that means the oxidation stage of cobalt has changed. And that means, as it's an oxide, very likely, well, you change the stoichiometry, right? You get ion migration, you get oxide migration between eventually the substrate and this layer. In the same experiment or similar measurement with the same intention was carried out at Petra Synchrotron in Hamburg at a hard X-ray photo emission spectroscopy beamline. So you come in with a hard X-ray beam and you measure emitted photoelectrons with a hard X-ray, which means many kilo electron volts, eventually 10, right? And so the energy of your electrons is so high that they can also escape from a few 10 nanometer deep sample. So you can rip off electrons also from the strontium cobaltate layer. And here again, there is, if we then make an energy loss spectroscopy, right, we are sensitive to the electrons that have been ripped off from the cobalt if we are around the cobalt edge again. Here's just electrons. And again, if we apply a voltage, right, we see this shift of the peak at the cobalt edge, which means indeed we are getting a change of oxidation state of all cobalt atoms, which means you get a kind of homogeneous, applying a bias, we get oxygen migration and a homogeneous depletion in oxygen of our layer and eventually feed it back when we reverse. So this is quite interesting because if we apply a bias and we get a change in resistivity, it is often due to channeling effects and filament formation, electromigration, which are non-reversible. This is more a degradation process than anything reversible. But ion migration that is homogeneous through the entire layer is reversible. So that means this material is a good material for resistive switching. And of course, details, everything is fully reproducible. This is very nice. So now I'm at the end of my 20 minutes. I hope I showed only a very tiny amount of examples of what is possible, right? And I hope you liked it and you'll join our 35,000 strong user community. And I also hope you stay here for the next 20 minutes where Marta Mirolo will speak about batteries and energy storage. Thank you.
Thank you very much, Tobias, for the introduction, and Eva as well for the introduction. So I will share my screen. Okay, so my name is Marta. I'm a junior scientist. I'm working at the ESRF, and I'm very happy that I have the opportunity to talk about in-situ and operando characterization, and especially what we can do in the energy sector. My background is on batteries, so I have a lot of examples on batteries. But I have also some other examples, not only on batteries. So when we talk about energy system and how we can investigate them in operation, what I'm mostly talking about is batteries, electrolyzers, and fuel cells. So how we can store energy, how we can convert it. I mean, we can in principle also include catalysis and synthesis, but I will not talk too much about that. But basically, what's the idea is you have devices, you have complex system in which you want to look at, for example, charge dynamics, because you might be looking at what happens during lithiation and delithiation in doing your battery operation. You might want to see if there are any inhomogeneities arising during operation. So these might be, for example, some salt precipitation in your fuel cell or your electrolyzer. You want to see at changes that are happening in real time, because these might be transient changes. So for example, in the case of catalysis and synthesis, you might have some phases that are forming at high temperature, for example, or under some specific gas environment or pressure. These are byproducts that might be transient. They might form during operation, but they might not be able to be stable if you disassemble your device, for example, to look into it with In-Situ characterization. And then, of course, like these are complex systems. We are looking at changes in potential, current, changes in the structure, in the chemical environment. But these are also devices that are complex, for example, electrolyzers and fuel cells. You need to inject gases, electrolyte, you have formation of gases or liquid byproducts. So these are quite complex devices that needs many different techniques to properly understand what's happening in them. I will start with an example on battery, where we looked at the charge dynamic during the operation of this battery. And what I will focus on is the lithium-ion battery, and in particular a way to increase the energy density by, let's say, playing with the chemistry of the electrodes, in particular the anode. So that's like where we store the lithium ion. Let's say traditionally we are using graphite, which is a very good anode material because it can store a good amount of lithium. It's very stable, like works for a long time. But there are materials that might be better, but we cannot use them fully. So silicon and like similar materials is an example, because these are materials that can store in principle much more lithium than graphite. The problem is that their volume expansion, so the way that they expand, the particles expand, is hindering their use as, let's say, pure anode material. So we cannot use them alone, but what we can do is mixing silicon and graphite. So the electrode, so the anode of these lithium-ion batteries, is maintaining the mechanical stability provided by graphite, but we are increasing the storage capacity, so the specific capacity of the electrode, by adding some percentage of silicon. There's a lot of research on that, and what we wanted to look at the new composite electrode, this graphite, mixture of graphite and silicon. And then when you have a new material, what you want to know is like basically you want to know everything about it. So we want to see how this composite gets lithiated, because we don't know if the lithium intercalates in the graphite and silicon together, or it goes first into one material and then shift to the other one. So we want to know like what happens to this material. We want to know what happens during relaxation, because that's a pretty important part of the battery life. So we charge and discharge batteries, but we might also take our battery and just leave it on the shelf for a while without using it. So there's no circuit, it's not connected. But so the question is, what happens during relaxation? Are the charges staying like where they are, so stored in graphite and silicon, or what happens? Is there any shuffling between graphite and silicon and so on? And we want to know if there's any kinetic limitation, because if we are lithiating and delithiating, we want to know if we can do it fast or not, basically. So what we are interested in is the charge dynamic in these new composite materials. And how we can investigate that? We need a technique that gives us information from both graphite and silicon simultaneously, and Operando, because we want to see what happens during lithiation and delithiation process, and with a good spatial and time resolution, because we want to see what happens at specific point in the lithiation and delithiation curve, but also in specific parts of the electrode. So what we can do to solve this problem is to investigate this composite electrode with scattering techniques such as wide angle and small angle X-ray scattering. So wide angle X-ray scattering is basically X-ray diffraction. We are looking at crystalline structure, so that's perfect for investigating graphite. It's crystalline material. We can look at the Bragg position, the Bragg peak, so we see how it's shifting, how it's moving, and this gives us information about the lithiation state of graphite. And then we can use small angle X-ray scattering, in which we are looking at like nanometer like structure, like in the nanometer range. And this is actually an information from the silicon domains, because silicon, as I mentioned, is swelling during operation. So the distance between these domains is changing. And since it's in the nano domain, we can track this with SACs. And then by looking at SACs, we can get information from the lithiation state of silicon. And then combining wax and SACs, we get the full picture of the charge dynamics in this graphite silicon composite. And then we can do, let's say, another thing that is like combining wax and SACs in computed tomography way. So basically, we are looking at the at slices of the electrode. So we are looking at 2D information. So we are getting spatial information about our electrode. And then what we can see is, for example, we see that graphite gets lithiated first, while silicon is only lithiated in a second moment. But what we can also see is that graphite and silicon don't get lithiated in the same areas of the electrode. What we can also see is if we do multiple cycling, so here it's, for example, the first lithiation, here is the second lithiation, what we see is that is actually they look kind of the same. If we look like this position T3, T6, they can overlap, so they are overlapping. So what we see is that the lithiation of this composite electrode is occurring following some reproducible pathways. What does this mean? Basically, we have 2D data sets of like the lithiation and delithiation process of this composite electrode as a function of time, because we are looking at them in Operando. And this is very powerful database because that's can help us to predict the life of this battery, because the fact that we are always stressing, let's say, the same areas of the electrode, and we are stressing graphite first, silicon afterwards, and so on, give us information that we can predict where the battery will fail, because the parts that are stressed more will fail earlier than others. This can help us to have better engineering of the electrode so that we can avoid earlier failure. We can also go a bit deeper into the analysis, because what we see, like looking at these slices, is basically what happens, for example, during the relaxation. I mentioned that relaxation is important for batteries. So what happens is, if we look at these 2D images, what we see is that during the relaxation process, so during the relaxation time, we see that graphite is losing lithium, so it's getting delithiated, even though it's unconnected, it's disconnected from the circuit and everything, but there's still some charge dynamic. So graphite is losing lithium, while we see that silicon is actually gaining lithium. So there's this interchange between graphite and silicon. But we can go even a bit deeper into this data analysis, because we perform some vertical scans across the electrode. So we can see what happens when we are looking at parts of the electrode that are close to the separator and close to the current collector. So when we do that and we look at how the lithiation of graphite evolves in time during relaxation, we see that graphite is pretty much homogeneous. So it's losing lithium, as we saw from the 2D slices, but it's losing lithium pretty much homogeneously across the electrode. There's no gradient of lithiation. Completely different story for the silicon, is a bit more complicated, because when we start the relaxation, we have highly lithiated silicon close to the separator and poorly lithiated silicon close to the current collector. But then with time, while the battery is, let's say, in this relaxation mode, we have a tendency to homogenization. So the silicon that is close to the separator is losing lithium, which is gained by the silicon that is close to the current collector. So we have this very complex charge dynamic that is occurring not only during operation, but also during relaxation, while we wait for example, dismounting our battery for ex-situ measurement. So that's why it's very important to investigate these devices In-Situ and Operando, because otherwise we would completely miss this charge dynamic in this kind of composite electrode. So talking about the charge dynamic, if we think about a bit more complex systems such as the electrolyzers and the fuel cells, where you have like flow of electrolyte, flow of gases inside and so on, then like this really shows the need for multiple analyses to understand what happens in these devices. So in the case of the electrolyzers, these are devices that are used, for example, for CO2 conversion, in which we have like the flow of electrolyte on one side, we have the gas flow on the other side, and what we want to obtain is, for example, some ethylene or some carbon byproduct that is much more useful than CO2. However, what happens is that we might have, for example, excess of water, so the water might block the pore for the CO2 flow, and which means that in our system we have less CO2, and this shift, there's a shift towards hydrogen evolution reaction. I mean, hydrogen is still very valuable, but that's not what we wanted to obtain. So we have to understand how this water flooding is occurring. We have also something else that can happen is if there's a change in pH, which might be due to some, for example, anion shift in the device. This again is reducing the amount of carbonates that is present, which again is that we observe as a shift towards hydrogen evolution reaction. So these are effects that we would like to understand better because we want to avoid them. We want to obtain our ethylene. So how do we investigate this factor? We have water management, we have the formation of precipitates, so these carbonates. We want to correlate these with potential fluctuation that have been observed. And of course, what we need to track is the gas evolution, because at the end, that's what we are interested in, is like to see if we are producing ethylene, if we are producing other carbonaceous gases, or if we are producing hydrogen. So we need to track all these parameters together. And the way to do that is combining, for example, X-ray diffraction, wide angle X-ray scattering, where we can look, for example, at the formation of precipitates, so salt formation. These are carbonates, and we can, for example, see that during operation, we indeed see the formation of these bicarbonates in the porous layer. What is also important is to see which kind of salt is formed. And in this case, we see that there's no formation of potassium carbonate, but only of these potassium bicarbonate. So that's important to understand what's happening into our device. And then we can see how this actually salt, how the presence of this salt is evolving during operation. So here we see the potential evolution. As I mentioned, there are some fluctuations which were not understood. So this is instead the evolution of the salt in our porous layer, and we can correlate the oscillation with the formation of these salt in the porous layer. We can also correlate them with the presence of water, because we can look at the water content by looking at the background basically of our signal, which is correlated with the water signal. So basically we have all this information together. So we get like the water presence, the presence of precipitates, the oscillation in potential, the gas evolution, and so on. And then we put all of this together, and we see that actually all of this is correlated. We have formation of this bicarbonate, which leads to the blocking of the CO2 path, which leads to increase of hydrogen evolution reaction, and so on. Basically, this is like a chain reaction, which at the end leads to the flooding of the gas diffusion electrode, dissolving the salt that was formed at the beginning, and then again leading to accessible CO2 in the device, and so on. So we have this oscillatory behavior, which we could explain only by combining all these different techniques, scattering, gas evolution, and potential evolution, and so on, putting all of this information together to explain this complex behavior. In the meantime, like we developed also a bit like further this project, and for example now we can also look at how the ions are shuffling in the electrolyte, so we can look at the X-ray fluorescence signal for that, and we can also look at the membrane porosity, which gives us information about the anion that can travel through it by looking at the small angle X-ray scattering. So you see how many different operando technique we need to understand these complex devices. So I gave you like a bit of more detailed let's say information about how to investigate these complex devices. I will give like some more information about different techniques and different projects that have been carried out, because I think that's interesting to see how many things actually we can see when we use a synchrotron radiation, how many different projects and how different materials we can look at. This is an example. This safety test that is performed on battery is a nail penetration test. So basically we have the nail that is penetrating the battery, and with radiography, with fast radiography, we can see how the different layers, so the different electrodes are first bent, then they are breaking, they are cracking. Here we start to see some breaking of the walls. We see like particles evolving, so we have gas that is being released and so on. And this can be done thanks to high energy and high photon flux synchrotrons. This is the case of ID19, is a very unique beamline where they can do this measurement at, like, with high spatial resolution and high time resolution. So we can see, for example, how this battery is being basically broken, and this give us information on how to make better batteries or safer batteries in the future, because if we change, for example, the chemistry or the composition, the engineering of the battery, we can avoid, for example, this thermal runaway, the gas release, and so on. Staying in the safety of the battery, this is like a study on solid-state battery. These are foreseen to be the battery of the future for higher energy density and higher safety, because they don't contain a liquid electrolyte. Instead, they contain a solid electrolyte, in this case, some sulfide solid electrolyte. And what we want to understand is how the active material behave with this new electrolyte. So this is like a cell that has been designed specifically for tomography studies. And this study has been done in situ. So we cycle the cell, we stop at specific state of lithiation, delithiation, or potential, and we look at what happens at the particles inside. And here we can see we have our active material is copper sulfur particle. We can track the phase evolution, so this gives us information about how the particle is being lithiated and delithiated. We can look at the morphology, so we can see, for example, the formation of cracks in the particles. We can see if the particle is, for example, so cracking, as I mentioned. We can see if it's swelling, if it's moving. So these are all information that are retrieved from this tomography study. And this one in specific was performed at BESI 2, which is the synchrotron in Berlin. We can also change, like, study different chemistry. So this is the case of the sodium-ion batteries. Again, like, these are batteries that are considered as an alternative to lithium-ion batteries for their cost, for the abundance of their materials. These are, let's say, relatively new, like they've been studied in the past decade, I would say, these batteries, but they are entering the market very quickly. We already have like some power tools that are powered by sodium-ion batteries. We have small vehicles like the scooters or the electric bikes. So the thing is that we need to understand what's happening in these new materials. And this is the case of this vanadium phosphate. Is very good material for sodium-ion batteries, but it's very complex. Like the oxidation state of this vanadium center is changing a lot during operation, and we need to understand how this is affecting, how the change in oxidation, how the local environment is changing during operation. And that can be done with X-ray absorption spectroscopy, for example. This is a study coming from Soleil Synchrotron in Paris, where they looked at the vanadium in specifically, and how this is evolving during operation. So we see how the different phases are evolving, and this leads to a better understanding, better designing of material, and so on. So it's important to study, for example, batteries, but also electrolyzer, fuel cells, energy devices in general, to prolongate their life, to make them lasting longer, to make them cheaper, safer, and so on. But we also have to think about the end of life of these systems, and so the recycling of batteries and electronics becomes more and more important. And that's a lot of research going on that. This is a case of, for example, using Prussian blue analog. This is a material that is very used, for example, in sodium-ion battery, but can be also used for recovery of the transition metal, for example, from spent batteries or electronics. So the idea is that instead of intercalating sodium, as in the previous case, we are actually intercalating the transition metal. But we need to understand at which point of the potential curve or at which condition we are intercalating which transition metal. So we want to selectively be able to intercalate manganese, cobalt, nickel, instead of having a mix of all these transition metal. So this was a study performed within the Remade Atari project at ESRF. So this is like dedicated to circular economy. And the results show that we can actually find out when and like in which condition we can selectively intercalate nickel, manganese, cobalt, and so on. So very interesting study. So basically what I wanted to show is how we can use synchrotron for advanced characterization in the energy sector. Why we need a synchrotron is because we can look at small details, we can look at unstable byproducts, we can look at fast changes in the sample. So all of that is perfect for in situ and operando characterization. Multiple techniques are available at the synchrotron. That's what also Tobias was showing. We can obtain morphological information, chemical structural information. We can combine all of these information with complementary techniques, because then we can really get a full picture of what happens inside our devices. Inside our complex devices. That's an important thing. And I didn't mention that, but synchrotrons are open to both academia and in the industrial use. So we can really look at cases that goes from fundamental science up to real industrial cases and real batteries, as the case here that is running next to me. So this is a real battery that we can look into it, and we can help companies to design better batteries. And that's all from my side, and it was really a pleasure for me to be able to share with you this information.
Thank you very much, Marta. Thank you also very much, Tobias, who I still see here in the presence list, and you see all of the clapping hands coming up. So a lot of interest and a lot of applause for you. We have actually 2 questions. Oops. Oh no. No, it cannot look at the questions. There they are. Okay, one coming from Devu. Early on, I think this was during your presentation, Tobias. What is the advantage of using bunch of electrons from synchrotron over in situ transmission electron microscopy experiments?
Well, there's a decisive difference, right, between the 2 techniques. What I showed is that the devices we looked at, right, while they're operating, you can't do transition electron microscopy on them, right? It's a system where the active layer is a few hundred nanometers below the surface. There's no way you can do this with TEM, and you need sample preparation for TEM, right? We don't need sample preparation. So this is essentially it. Quantification of 10 to the minus 6 strain, I don't think that's possible with TEM today either. So the examples I showed, also the germanium laser, the switching on, a few 10 Kelvin temperature difference seen from lattice expansion, there's no way you could do this. And anyway, the intact device, which is several micrometers large, 3D, you cannot look at that with TM. Sorry, Eva, you're muted.
Yeah, makes a lot of sense. Thank you. There's a second question from Maria Fernanda Betancourt Soto. Could in situ synchrotron characterization be used to study carbon fiber reinforced polymer composites under cryogenic conditions, focusing on microcrack formation and fiber matrix interface changes?
I would say yes, maybe not with diffraction, but there's 2 ways. There's radiography is always possible. Phase contrast and nanotomography should work. All depends on the spatial resolution and the time resolution you need. This is, of course, very quickly a vast parameter space to be clarified, but with phase contrast imaging and nanotomography can look at the sub-100 nanometer resolution. Of course, if your fibers are, typically carbon fibers are in that range, that is observable. Depending on the size of the cracks, when you speak about crack formation as well.
Okay, so then we have another question here from, first of all, an organizational one, whether you would be willing to actually share the slides with us and the attendees. So for your information, we had up to 115 people, but we can also clarify that later. And then we have a question from Ana de Oliveira. Marta, you mentioned the importance of multimodal for characterizing materials at work. Did you do every technique separately, or was there the possibility to combine quasi-simultaneous experiments?
So in some cases, we can combine them. So the case of SAX, wax, X-ray fluorescence, we can do it simultaneously or quasi-simultaneously, depending a bit on the case. There are beamlines that are dedicated to combined XAS and XRD. So it depends a bit on what you want to combine. If you want to combine XPS with tomography, I would say no. You need to have like two different experiments. But if you want to combine high energy scattering like wax, PDF, SAX, that's possible. If you want to combine XAS with XRD, might be possible. So yeah, so it depends a bit on the technique. And then in Synchrotron, basically what we tend to do is we take or if we can, we take the setup of users. So they might come with their GC, MS, or with any extra analytical tool. I know some beamlines are adding Raman spectroscopy, because then they can do, for example, X-ray absorption spectroscopy combined with Raman spectroscopy. So we tend to add as many techniques as we can in one experiment, because then we can really correlate all the information. It's not always possible. It depends on the instrument, and it depends on the experiment.
And I think, Marta, that already sort of gave a nice introduction to Anna's second question. Where do you see the biggest bottlenecks at the experimental side? I think you more or less already just answered that, but I'll let you have another go at this.
I think like being able to combine as many techniques as possible, like in one go, that would be ideal. The bottleneck might be then the data analysis, because we are acquiring so much data from one single experiment. In Operando experiment, like Operando experiments are really producing tons of data, and then being able to analyze them, to analyze deeply the data, then might be the bottleneck. So we need more manpower basically to run the experiment, to analyze the data, to understand the data, and to share the information. I don't know if Tobias has a different view on bottlenecks in the synchrotron experiments.
No, definitely not. But we will. I mean, we're working on this. Much of this can be done by improved software, right, and handling of standardized software, which we're trying to standardize across light sources, of course. Yeah.
Okay. Then we have one, I would say, last question, also looking at the time, from Ricardo. Are there any data about application of wax and SAX to the in-operando diagnostics of bigger ion intercalation into graphitic electrodes?
SAX wax is quite used for lithium-ion batteries. So there's quite a lot of publication on the use of SAX wax for graphite investigation in coin cell, in pouch cells, in swage lock cells. I think also in some commercial cells. So it's possible, and there's total information in the literature.
Okay, so Ricardo, go and dig into the literature from what I hear from Marta.
ID31 also published some papers on graphite, so you can have a look.
Yes, maybe start there. Exactly. So I have one new comment, thanks, from Ricardo to everybody. So with that, I think we have come to the end of this very, very interesting webinar. Join me again in thanking both Tobias and Marta for their introductions and then in-depth presentation of multiple examples. I would like to invite everybody, of course, to stay tuned, follow us on our social media, and definitely also look out for the next emails. We will be definitely having another webinar before the summer break, so meaning in July. We're not 100% sure yet on the topic because we're trying to find something that is both timely and of interest to the community. As you know, we always switch a bit between technical, political, these kinds of things. But stay tuned and join me again in thanking the speakers, and enjoy the rest of a lovely Friday. Thank you.
Thank you all for
Thank you for
the
coming.
participation.